This is the fifth in a series of lessons about string matching algorithms and how to implement them. In the previous lesson, you learned about the pattern pre-processing phase of the KMP algorithm. You learned exactly what information about the structure of a pattern is captured before the search begins. You also learned that this information is stored as a set of LPS values in a partial match table, which is accessed frequently during the KMP search. In this lesson, you'll learn how to generate the LPS information for any pattern programmatically. In the previous lesson, you saw how to construct a partial match table by inspection. You should therefore be able to come up with a set of LPS values for this pattern by yourself. If you're not sure how, please review the previous lesson before continuing. Here are the LPS values for this pattern. We're going to develop some pseudocode to generate them systematically. I've chosen this somewhat abstract-looking pattern because it will help us to build a program that can handle any possible combination of characters. And don't forget, pattern matching is not just about word processing. These letters could represent signals being transmitted on a network, or a sequence of biological molecules. In essence, we need to examine every possible partial match and attempt to identify its longest proper prefix, which has an identical suffix. For example, suppose we are considering only this partial match. The proper prefix of 4 characters, AA, has an identical suffix of 4 characters. This is the biggest possible prefix with an identical suffix, so the LPS value is 4. We could use brute force to obtain this value. This would involve comparing the 1-letter prefix with the 1-letter suffix and making a record of the LPS value. We would then compare the 2-letter prefix with the 2-letter suffix and then replace the LPS value if it was bigger. We'd then look at the 3-letter prefix-suffix combination followed by the 4-letter prefix-suffix combination, replacing the LPS value if it was bigger. The brute force approach would need to compare every possible prefix with its corresponding suffix. To achieve this programmatically would require a loop to scan every possible partial match. We've only looked at one here. We would also need a loop inside this loop to visit each prefix and its corresponding suffix. A partial match of 9 characters has 8 prefixes and 8 suffixes. Then another loop inside this one to compare each prefix character with its corresponding suffix character. A loop within a loop within a loop would result in a program that runs with cubic time complexity. In other words, doubling the size of the pattern would increase the time taken to process it by a factor of 8. A brute force approach would therefore be very inefficient for large patterns. I'll show you some brute force code later, but for now, let's look for a better way. The objective is to perform the minimum number of character comparisons with as little backtracking as possible. Furthermore, the program should run with linear time complexity. That is, doubling the pattern size should only double the time it takes to process. This means no nesting of loops at all. By the way, when it comes to building a partial match table, there is actually no need to store the pattern inside it. The KMP program is already storing the pattern in a separate string variable. All that really needs to be stored is a set of LPS values. So these can be stored in a one-dimensional array variable. We'll call it the LPS array. The zero-based index numbers of an array provide a convenient way to refer to the positions of the individual characters. To help us see what's going on, we will show the pattern above the LPS values, for now. So how did Knuth, Morris and Pratt do it? What is it that makes the pre-processing phase of the KMP algorithm so clever? On the right-hand side, you can see some pseudocode. We're going to step through this while visualizing the process. The program makes use of two variables, one called len, which is short for length, and another called I. I is used to define each possible partial match. It only ever moves forwards. I begins at position 1, defining a partial match that includes the first two characters. The variable len tracks the length of the longest prefix with an identical suffix of the partial match under consideration. Exactly what this means will make sense as we proceed. A partial match of only one character is trivial because it has no proper prefix and will therefore always have an LPS value of 0. This value can go straight into the LPS array. The main loop of the program examines the two-letter partial match first, as defined by the position of I. The remainder of the pattern can be ignored completely for now. Through inspection, we can see that this partial match has a one-letter prefix and a one-letter suffix, and they are identical. So the LPS value must be 1. To determine this programmatically, we use the values of len and I to refer to the first and second characters of the pattern, and we compare them. If the characters are the same, len is advanced to index position 1, which gives us the LPS value we need. This is saved into the table and will now never change. By the way, the LPS value for a partial match of two characters could only be 1 or 0. The value of I is incremented, and the focus is now on the next partial match. At a glance, we can see that the LPS value must be 0, but to obtain this programmatically, we compare the characters at len and I to discover that they are different from each other. What happens next is rather clever. I should say that it won't be immediately obvious why we are doing this yet, but I will go through the reasoning in detail shortly, when we've processed more of the pattern and it's easier to understand. For now, suffice to say, we are going to take the LPS value of len minus 1, that is the LPS value at index position 0, which is 0, and move len back to this position. We then compare the new pair of characters at len and I to discover that they too are different. The value of len is already 0, so it can't move any further back. It has to stay where it is, giving us an LPS value for this partial match of 0. I is incremented, and the next partial match is under consideration. The characters at len and I are compared and found to be different. As before, len can't move any further backwards, so it stays where it is, and an LPS value of 0 is recorded at position I. I then moves forwards, defining the next partial match. The characters at len and I are compared and found to be the same. This means len can advance, and an LPS value given by the new position of len, 1, can be saved in the array. I advances to isolate the next partial match. This, by the way, is where we can really start to appreciate the beauty of the KMP preprocessing algorithm. The characters at len and I are compared and found to be the same. Len is incremented, and the position of len is saved in the array as the LPS value for this partial match. At a glance, we can see that this partial match does indeed have an LPS value of 2. What is so clever about this approach is it takes advantage of the fact that each partial match contains information about the next. Bear with me, and this will become clearer as we proceed. I is incremented. The next partial match is under consideration. The characters at len and I are compared, and they are different. But we are not done with this partial match yet. Len moves back to the position given by the LPS value of len minus 1, which is 1. Bear with me, you'll see exactly why we did this in a moment. a new pair of characters are compared, and they are the same. Len advances. Another LPS value is saved. And I advances to the next partial match. Another pair of characters are the same. Len is incremented, giving us another LPS value. Notice that as the processing continues, the LPS values only ever increase by one at a time, but they can drop suddenly. This gives us a clue about the insights that led to the creation of the KMP algorithm. It suggests that there is a relationship between successive partial matches, a relationship that we can take advantage of. After a long run of successful comparisons, we have a pair of characters that are not the same, requiring that we move Len backwards to a previous position, a position given by the LPS value of Len minus 1. Let's take a closer look at why this is what we need to do. Carefully examine the previous partial match, that is, everything up to and including index position 10 of the pattern. And you'll see that the current value of Len, namely 6, is the number of characters in the longest prefix with an identical suffix of the previous partial match, that prefix being AABBAA. Of course it is. That is the LPS value that we've most recently saved. Now, it's not immediately obvious, but look closely at just this prefix, and you'll see that it has an LPS value of 2. This information is already in the array. It tells us that the first 2 characters of the prefix, AA, are the same as the last 2 characters of the prefix. So what? Well, if the first 2 characters of this prefix at positions 0 and 1 are the same as the last 2 characters of this prefix at positions 4 and 5, and if the 6-character suffix of the previous partial match is the same as this prefix, which it necessarily is, it follows that the first 2 letters of the suffix at index positions 5 and 6 must be the same as the last 2 letters of the suffix at positions 9 and 10. We can therefore deduce, for a fact, that the characters at index positions 9 and 10 are the same as those at index positions 0 and 1. So we don't need to check them again for the current partial match. Hence, the new position for Len should be the 3rd character along at index position 2, to exclude the characters that we know for certain are in the prefix and the suffix of the current partial match. At this stage, then, the new value of Len is given by the LPS value of Len minus 1. The processing continues. Yes, generating a set of LPS values for a pattern in this way is complex, and it can be challenging to fully appreciate how it works. But remember, it took some of the greatest minds in the fields of mathematics and computer science to create the KMP algorithm. Even they struggled with it, and they were building on the earlier work of others. The beauty of the KMP preprocessing algorithm is that it has only one loop with no nested loops. This means it runs with linear time complexity. In other words, doubling the size of the pattern will only double the time it takes to process it. Now let's take a look at some real code. Here's a VB.NET program which takes a brute force approach to generating a set of LPS values. It considers each partial match individually to calculate its LPS value. It looks at each prefix-suffix pair to see if they are the same. So for each partial match, it looks at the 1-letter prefix and compares it with the 1-letter suffix. It looks at the 2-letter prefix, compares it with the 2-letter suffix, and so on. When all the possibilities have been checked, it moves on to the next partial match. I've declared a number of variables to begin with. First of all, we've got the pattern string itself, and then the LPS array. And I have a number of additional variables here, which I use during the process. A partial match of only one character has an LPS value of 0, so this can go straight into the array at index position 0. Then the program begins in earnest. The outer loop scans each partial match one at a time, starting with the smallest. We have a couple of variables to store the LPS value. Notice we've got a temporary variable, which will temporarily hold the LPS value until we find a better one. To isolate the partial match, I'm using the substring method of the pattern string. You could say that I'm cheating a little bit here by using a built-in method. But if I didn't use the substring method, I'd be writing a lot more code. Now, for each pattern, I need to isolate each prefix and its corresponding suffix. So that's what's going on here. And again, I'm using the built-in substring method to get a hold of that prefix and to get a hold of its corresponding suffix. This is where it's starting to get a bit fiddly. My innermost loop is comparing each character of the prefix with its corresponding character of the suffix. Every time we have a match, we add 1 to the temporary LPS variable. If we have a mismatch, it means that the prefix doesn't match the suffix, so we reset that to 0 and we stop looking. We exit the for loop. If the temporary LPS value is better than the one that we've already got, then we replace the best LPS value with the temporary value and then reset it in readiness for the next prefix-suffix pair. When we've checked every prefix and corresponding suffix for a given partial match, we can put the LPS value into the array and then move on to the next partial match. This implementation uses a loop inside a loop inside a loop. This means it has cubic time complexity. If I double the amount of data, in other words, if I double the length of the pattern, then it's going to take 2 times 2 times 2, that's 8 times longer to process. To get a sense of just how clunky this is, I'm going to put a breakpoint on this outer loop and then start stepping through the code. You can see that with each pass of the outer loop, as the partial matches get bigger, the number of times that the innermost loop has to run is dramatically increased. Let's take a look at the LPS array in the watch window. So far, I've only got to the 4th possible partial match. There's a long way to go. I think I'll stop it there. Let's put a breakpoint at the very end of the program and take a look at the finished LPS array. Well, those are the values I was expecting. But imagine if the pattern was twice as long, how much extra processing would be necessary? It's far from ideal. Here's the same program in C#. It does exactly the same thing, in exactly the same way, and it has the same limitations. The only difference is the syntax. And here's the same program in Python. Again, it does exactly the same thing, in exactly the same way, with exactly the same limitations, if not more, because Python doesn't handle memory particularly well. Now here is a much more elegant implementation for generating a set of LPS values. The VB.NET code looks almost identical to the pseudocode that you saw earlier. The key thing about this program is there is only one loop. There is a little bit of backtracking, but it runs with linear time complexity. Doubling the size of the pattern approximately doubles the time it takes to process it. There's my LPS data. I'm just going to move this code into a function so it can be called at the start of a KMP search. The function has one parameter, the pattern, as a string, and it will return an array to the program that calls it. Now let's write a simple program to call the function. I need an array to hold the LPS values that are returned. An array of integers. And here's the call. Let's make sure it works. And that looks fine. Here's the same program in C#. The only difference is the syntax. And here's the same program in Python. In the next lesson, you'll learn how to write a program to perform a KMP search. A program that makes use of this pattern pre-processing function before it begins.